we went on to talk about standard deviation. Standard deviation of a set of numbers is a square root of the mean of the squared deviations from the mean. Now that's not quite true. This is, though, true if you got over 30 numbers. And I'll say if n is greater than 30, n is how many numbers you have. Okay, if n is less than 30, then you want to subtract 1 when you calculate the mean of the squared deviations. And we'll maybe talk about that. Actually, maybe talk about it in terms of the formula, because there is a formula. Okay, now I bring this up at this point because one student used a formula, basically used this formula, and there's nothing wrong with that formula at all, except maybe the way I've written it. I've got n in the denominator here, and if n happens to be less than 30, this should be n minus 1. Now, I don't want to get into all the details of why that's n minus 1. It's because you just get a better approximation to the normal curve if it is n minus 1. But there are reasonably deep mathematical reasons for that that are beyond what we can talk about here. The notation people were used to, I used xi minus x bar, which is a very standard notation. And some people say, well, there's a different symbol there, and they described it. Well, the symbol was mu, which is another standard symbol, the Greek letter mu. It's a standard symbol for the mean. X bar or mu would be the mean of the set of numbers for which you're trying to calculate the standard deviation. The other symbol that you probably saw then is sigma, lowercase sigma, Greek sigma, and that is the most standard way to notate a standard deviation. Sometimes people will use S. Sigma is really probably a little better because S has so many other connotations. Okay, so what we want to do by way of illustration is we're going to calculate the standard deviation of a set of coin flips of the number of heads that you would get if you did 16 coin flips and they came out with exactly these results, maybe in a different order, but with these results. So that you would have 0 heads occurring 1 time, that's when you get all tails. You'd have 1 head occurring 4 times when the head is here or here, there's another one in here, here, or here. Okay, so you have 4 of these. Now, of course, if you list by the number of heads, you can see where the 1 head occurs, which would be here, 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 or here, one of these 4. So there are advantages to both ways of listing. Okay, for 2 heads, you can count them. Over here, it's easiest to see there are 6, but you can spot them here just as well. There's 2 heads, there's 2 heads, and there's 2 heads, and then there's 2, and there's 2, and there's 2. Okay, that makes 6. Then 3 heads will occur 4 times, 4 ways, and we can see those being the ones where we have 1 tail, and we can find them on this listing also. And then 4 heads occurs 1 time at the beginning of either of these listings. Now I'm going to flip out boards here, except I'll say that then the ideal histogram for flipping 4 coins would look like this. Okay, you have 1 way to get 0 heads, and I guess maybe I'll label that. I don't like to take up a lot of extra time on the video, so actually I'm going to pause and do that labeling just to save you a little time. Okay, I've written the 0, 1, 2, 3, 4 heads. I got a £, H, which stands for the number of heads. Put a £, in front of this one too. I didn't have one there just to be consistent. Okay, so you have 1 way to get to get 0 heads. So there's 1 way to do this. There are 4 ways to get 1 head. Let's see if I do this 4 times. 1, 2, 3, 4. Looks like it works out. about right. And then 1, 2 more makes 6. That's the number of ways to get 2 heads. Then 4 ways to get 3, 1 way to get 4. So that works. So now we have this histogram that we can compare with the shape of this histogram. We don't care that one is bigger than the other. We're just looking at the shape. And we see that this one is completely symmetric, and this one, it has a lot of symmetry. And you would not expect it to be completely symmetric in a real trial where you're actually flipping coins. But random things can happen. You can't determine exactly what's going to happen. Now, if we flipped a large number of coins, if we flipped the 4 coins a large number of times, let's say we did it 1,000 times, the shape of the histogram would be much closer to the shape of this one, or at least we would expect that the shape would get a lot closer. This is the ideal, and this is actually what's going to happen if you do an infinite number of trials. The shape of the histogram has to approach this shape. I'll also comment that the definition I gave you of standard deviation was in words here. Okay, this is the definition you were given. This is a definition that you might well have seen in your textbooks. If you've had Algebra 2, certainly you've probably seen this, maybe even in Algebra 1, and possibly even in 6th or 7th grade. I think my grandson saw this in 6th grade or 7th grade, probably 6th grade because he's doing Algebra 1 in 7th grade. And I think he did this before Algebra 1. In any case, so it would be natural to go ahead and use the formula. The person who used the formula did a good job of applying it, except the person didn't square this quantity and then got 0 for the standard deviation as a result. And you can think about why if you didn't square this quantity, you would get 0. The sum of the xi minus the means, sum of your x values minus the means would be 0, so that the whole thing would become 0. But we want to talk about deconstructing this statement, and then we can talk about how this statement is equivalent to this definition. It's a little deeper idea. Why is this statement equivalent to this definition? I leave that as a question that you should ponder. To use that formula, you should understand what the formula means, and to understand what the formula means, you really pretty much need to understand how it's related to this verbal description of the formula. Or rather, I should say, this verbal definition of the standard deviation. This is a perfectly good mathematical definition. This is completely equivalent to this, so one is not any better than the other, but understanding them both is a key to deeper understanding.